Assalamualaikum and a very good day. My name is Aliah, and with my fellow friends Najihah and Sofeeyah, we are from Group 4. We will be presenting about design and optimization of a 128-point fast Fourier transform using high-level synthesis. We all know that standard CPUs are too slow for real-time signals because they handle heavy FFT methods step by step in a single line. So our team used high-level synthesis to turn C++ software into a fast parallel hardware circuit on an FGPA, giving us a high-speed accelerator perfect for edge device.
Assalamualaikum, my name is Najihah. So for task 1, we started with Python to benchmark the FFT. So we used the given 10 MHz sine wave signal and apply 138-point FFT. In the time domain, the signal looked like a smooth sine wave. When we convert into physical domain, we saw a clear peak at bin5, which matched the expected frequency component. This confirmed that our FFT was working correctly. The execution time was measured. The Python complete one run about 0.0205 milliseconds. This is quite fast for software test, but it is still not suitable for real-time system that need continuous high-speed processing. So this step gave us a baseline result and helped us to understand the limitation of software-only FFT. In task 2, we moved from Python to C++. We started with a small 4-point FFT design and expanded into a 128-point FFT. The C++ code was tested using the same sine wave input and we verified the output against the Python result. The console output from VT/else showed that the result matched perfectly with very small error value. So this gave us the confidence that the algorithm was correct. However, the execution time on CPU was slower compared to Python, about 0.151 milliseconds. This showed that C++ is flexible and portable. It still runs sequentially on CPU and cannot achieve the parallelism needed for real-time edge device. This step was important to prepare for design conversion into hardware. Move on to third next was to synthesize the FFT design using VT/ls, where C++ code was converted into hardware description language. So it could run on FPGA. We set the target lock period to 10 nanoseconds, which is equal to 100 MHz. The synthesis report showed that the baseline design achieved estimated clock period is 7.3 nanoseconds, which is better than the target. So the maximum operating frequency was 136.99 MHz. The latency interval was 143 clock cycle, which means the design could process data much faster than CPU version. This step was very important because it shows how high-level synthesis can take a software design and turn it into efficient hardware logic. It also gave us the first set of performance number for FPGA implementation, which we later improved with optimization. Thank you.
Assalamualaikum and a very good day, Dr. Hadi. My name is Sofeeyah and I will be continue the video with the Vivado part. So here is for task 4. Our total power and temperature exceed the chip hardware capability. So in this project, we use the same chip as we used in assignment 1 and also as stated in the tutorial video. So for our task 4 here, the dynamic power is 115 watt and the device power is 4 watt. For the timing summary, our slack is 0. Our endpoint is 17,662. And the third main thing to look is the CLB LUT. Our LUT use is 11,005 and the DSP used for task 4 is 48. Later on, during optimization, we will see that all of this number will decrease drastically. Okay, so here is the optimization A, which is lookup table. So at the right top part, I put the task 4 value from the previous slide. So here, our dynamic power dropped very drastic. So now the dynamic power is 11 watt and the static power is 0.6. So our total power is 12 watt and our temperature also remain under the hardware limitation. So our slack is 0, same as previous one. But our endpoint also decreased, which is now 3,043 instead of 17,662. So now for our LUT, From 11,000 in task 4, lookup table managed to reduce the LUT to 1,204, and the DSP value used is now 16. So now we move to the second optimization, which is bit width optimization. Since our coding use a very large number of bit, so bit width optimization supposed to make it parallel. So the power in higher than the task 5A, bit width use more power compared to lookup table. So bit width use dynamic power of 14 watt and static power of 0.6, which is almost the same, but the dynamic power is higher, more 3 watt compared to the 5A. For the timing summary, the slack is still 0, but the endpoint slightly higher, but still between 3,000 to 4,000. So it is 3,614 for 5B. And for our LUT, it is much lower than 5A, which is 1,060. And also our DSP is lower too. It is lower by half, which is now 8 compared to 16 in task 5A. So this means that when we optimize our project, we use less FGPA resources, so lesser LUT and lesser DSP, but our power is higher because the bit width process, to make it parallel, it use a lot more power. So later in our report, it can also be seen clearly the difference with our design of FGPA usage between task 4, task 5A, and also our task 5B. So that's all from me. I will pass back to my groupmate, Aliah.
Thank you, Sofeeyah. Now we move on to task 5 optimization, where we apply 2 key optimization paths to our designs. As shown in table 1, introducing a memory lookup table in Op A cut our processing time, and adding parallel HLS prognosis in Op B gave us the fastest time of just 0.000310 milliseconds. Looking at table 2 and 3, Op B allowed the chip to reach a peak frequency of 336 MHz and a massive throughput of over 412,000 samples per second. We achieved all of this while heavily optimizing our chip area, dropping our logic gate count from 11,000 down to just 1,060 LUTs, and reducing our math engine down to just 8 DSP blocks according to our final routine. Now we move on as to why static and dynamic power does not change. Looking back at our tables, while our dynamic power dropped a lot from the baseline, the static power stayed almost exactly identical between 0.61 and 0.62 watt across all of our optimized tests. First, we must look at the silicon fabric limitation. Static power is the cause of simply being turned on. It is caused by transistor leakage that happens regardless of whether the chip is doing math or sitting idle. Because our baseline Opt A and also Opt B designs all use the exact same FGPA chip, the amount of leakage is fixed. It is an absolute hardware limitation of the silicon substrate itself that software optimization cannot change. Secondly, we realized that absolute value matter more than percentage. In our previous FIR filter project, the hardware layout changed drastically, which shifted the power ratios. However, the FFT is very rigid math network. Our optimization here were about the fine-tuning, the precision, and memory access rather than rebuilding the whole structure. The tiny 1% shift you see in our power shift is likely just statistical noise from the Vivado estimation algorithm. For the conclusion, this project successfully converted a C++ software FFT program into an optimized high-speed FGPA hardware circuit using high-level synthesis, safely reducing operational latency from 143 cycles down to an accelerated 31 clock cycles, while rescuing the hardware fabric from a dangerous 120-watt baseline thermal overload down to an efficient and stable 15.291 watt runtime profile. That's all from us. Thank you and Assalamualaikum.